I will talk today about representation theory for fusion categories. So let me first spend a couple of minutes telling you about fusion categories for those who maybe don't know exactly what that is. So here's a quick definition of a fusion category. Fusion category is well, it's a category which is a linear category, which I will always take to be over the complex numbers. And it is semi-simple with finitely many simple objects. So every object is a finite direct sum of simples. And up to isomorphism, there's only finitely many simples. So a typical example of such a thing that you all know of is, for example, the category of representations of a finite group. There's finitely many irreducible representations. These are the simples, and every representation is a sum of those. So then there is also a tensor product structure, which is present here. And here you see that the example that I just gave you about rep of a finite group is not a very typical example, because I'm going to only insist that this tensor product be monoidal, not symmetric monoidal. So for example, if I have two objects A and B, then A tensor B is not required to be isomorphic to B tensor A. So it's more like the analog of a group as opposed to being the analog of a commutative group. And then finally, and very importantly, there is a requirement about the existence of duals. So every object should admit a dual object with respect to this tensor product. And so I'm not going to write down the equations that describe what it means to be a dual, but let me just say it in words anyways. So an object A has a dual B if there's an evaluation B tensor A to the unit, and also a co-evaluation from the unit to A tensor B, satisfying so-called zigzag equations. But let me just leave it like that. So I will be caring specifically about unitary fusion categories, because these are the ones that are going to be relevant for the theory that I'm going to talk about today. And being unitary is extra structure on a fusion category. And the extra structure that we have is an involution. So if I have a morphism F, say F goes from A to B, then I postulate the existence of a morphism F star that now goes the other way around from B to A. And this needs to satisfy a couple of algebraic identities, namely, first of all, this is antilinear. I didn't write that down, but that's part of the axioms. Then F compose G, all that star is G star F star. And then for the tensor product, there's also a similar equation where the order is not reversed. And at last, there is a positivity requirement. And all of that has as a consequence that, so I told you about duals. Really, there's two ways of writing the duality equations, leading to a notion of left dual and right dual. But in the presence of this star, then any solution of the equation saying that B is a right dual of B of A can be transformed into a set of data that tells you that it's also a left dual. So left dual and right duals become the same thing, and the dual is denoted C bar, because in the special case, the most trivial case where we're talking about the category of finite dimensional Hilbert spaces, this agrees with the operation that sends a Hilbert space to its complex conjugate. And I'm going to think of that as a covariant antilinear operation going from an object C to its dual C bar. Now, I want to think of fusion categories as being analogues of groups where the requirement of invertibility has been weakened and has been replaced by dualisability. Of course, you can ask, well, what happens if I do have invertibility? So if I do ask that every object is invertible, as opposed to merely asking that they're dualizable, and then you get a special class of fusion categories, which happen to be in bijective correspondence with two groups, where there's a group here, which is the set of objects up to simple objects up to isomorphisms, and U1 is, well, if you know about two groups, a two group is a thing that involves a non-abelian group and an abelian group, and in this particular case, the abelian group has to be U1. So two groups somehow fit very closely into that story. I won't come back to two groups, so let's just leave it like that for those who know what two groups are. So let me come to the main topic of this talk, namely, what is a representation? We make a little bit of space and use that space to put here in the middle the main definition. A representation of a unitary fusion category C. So C here is the same C there. Is an action on, I didn't tell you what R is. R here is a von Neumann algebra. So you have to pick a von Neumann algebra, R, and then a representation is an action. So if on the category of R modules, so R modules is the thing on which C acts, and you can either think of it as being a tensor functor from C into bimodules, or an action on R modules. And these two perspectives are the same because the category of bimodules over R is the same thing as the category of endomorphisms of R mod. So for those who need a bit of a mini course on von Neumann algebras, here are the relevant facts that will allow you to follow what I'm saying today. Okay, so a von Neumann algebra is a type of algebra over the complex numbers, which is an algebra that can be represented by operators on a Hilbert space. So H here always refers to a Hilbert space. B of H is the standard notation used in this area to talk about operators. So the linear maps from H to H, which are also continuous, that's called B of H, because continuous in operator algebra, that's called bounded. So bounded operators from H to H, that's B of H. It's a very central object. And by definition, a von Neumann algebra is a sub-star algebra of B of H, which is equal to the commutant of its commutant. Here, this prime notation means take the commutant. So if R is a star algebra sitting inside B of H, and R prime is, by definition, the set of everything that commutes with R. So you take the things that commute with the things that commute with R. If that's the same thing as R, then you have a von Neumann algebra. And then there's a couple of standard definition. Suppose I have a von Neumann algebra which is not already represented in some B of H, then a module is a choice of H, and star algebra homomorphism. There's the same left equals right phenomenon that happens here. Left modules and right modules, you can go back and forth between a left module and a right module by replacing the space on which things act by its complex conjugate with this new action. Something rather non-trivial is the existence of a canonical bimodule associated to every von Neumann algebra. And finally, there is a somewhat intimidating looking formula that defines an operation called confusion, and which, apart from the fact that the formula is intimidating, behaves just like a tensor product. So yeah, that's it about the Neumann algebras. So now I claim that acting on R mod, acting on the category of R modules, is like a representation. So let me just throw at you a table of analogies that we can have a look at together to see if we like it. So let's see, what do we have here? So here I told you that a finite group G is what I'm going to think of as being the analog of my fusion category, C. And if a group acts on a Hilbert space, then a fusion category C acts on, so the analog in this row here, what we have is that the analog of a Hilbert space is this category here of R modules. And it's useful to think of it as a sort of abstract thing. So what is the abstract thing that this is? It turns out that it's a W star category. That's just a special type of category, which is the same thing as R mod, except that R mod, the R of R mod is not uniquely defined. Like you can replace it by something Morita equivalent and get the same category. So really I want to think about M and R. There's many different R's that can be used to describe the same thing. And one of the reasons why this is a good analog of a Hilbert space is that just like Hilbert spaces have an inner product with values in the scalars, so here the scalars should be replaced by the category of Hilbert spaces. So this is the categorical analog of scalars. There is a canonically well-defined Hilbert-valued inner product on any W star category. And here's a formula for it. I hope that it's big enough so that you can see X and Y map to Y bar confusion over R with X. And the interesting fact is that here I sort of picked an R in order to write down that formula, but this formula happens to be completely canonical and independent of the choice of algebra R that you pick in order to write M equals R mod. So it's really a thing that comes canonically together with M. Anyway, so once you have that, then you can look at the endomorphisms of M, and which is the same thing as bimodules, and a map into the endomorphisms is a representation. And unitarity, which is that equation down there, holds in this sense here. Let me reorganize things a tiny bit. So this one here is an important definition, so I want to keep it visible up here. Okay, great. Then just under, I want to say how and why we can think of there being some kind of representation theory going on there. So there's many situations where we can talk about things acting on things, but maybe not all of them deserve to be called representation theory. So in order for something to be representation theory, I'm going to argue that you need a little bit more. First of all, you need to have the possibility of faithfully detecting the object that you're trying to represent. For example, if I'm thinking about Lie groups acting on sets, where sets have the discrete topology, continuous actions, well, that notion makes sense, but it's not a very good notion because there aren't enough actions of Lie groups on sets which are continuous. So it's not possible to faithfully represent Lie groups, so that's not a good representation theory. And so in this context, because we're in a categorical context, faithful really means something a little bit stronger than you might think. Really, it means that this functor here, this action, C goes to Bim R, this functor should be fully faithful. So this is a property of the underlying functor, not of the tensor functor. And then the next thing that you want is for representations to be classifiable in some sense. I mean, this should be taken with a grain of salt. Not everything can be classified in representation theory, but there should be a feeling that, yes, I've managed to classify things to quite an extent in order for this to work. But this is, of course, relative to classification of von Neumann algebras, because after all, there's a von Neumann algebra here. So however much I can classify von Neumann algebras is going to be an intrinsic limiting factor to how much I can classify these representations, because the representation contains, as part of the data, one of these von Neumann algebras. So let me tell you a little bit about classification of von Neumann algebras. That's, of course, a huge body of work. So what I'm telling you about right now is the work mostly of Alain Connes and Uffe Hagerup, and that's what Alain Connes was attributed his Fields Medal for. So there's a lot of work here that I'm putting in one big slide. So first of all, von Neumann algebras are there's a sort of dichotomy between things that are so-called hyperfinite, that's a technical condition, and things that are not hyperfinite. And hyperfinite essentially means classifiable, or rather after the fact means classifiable. A non-hyperfinite is completely wild. And then there is every von Neumann algebra is a direct sum in some generalized sense of things of type 1, 2, and 3. And if you're hyperfinite, there exists a unique one in each one of these. Type 3, 0, there's many, but how many there are is, again, well understood. Whereas in a non-hyperfinite case, it is completely wild and hopeless. I mean, this is not a thing to try and classify. And now here's a theorem which it's a little bit tricky, like what I'm deciding to assign it to, because these people here haven't really written this theorem in this particular form that I'm giving you right now. But on the other hand, probably if I showed them this the way I've written, they would be like, oh yeah, this is what I've proven. So this theorem here has two parts. One of them says that if you have any representation, C to Bim R, one thing you can do is you can take the essential image of C inside Bim R, and you can call that D if you want, and by definition, D maps fully faithfully. And then there's this thing called the dominant functor, which really just means that every object of D appears as a summand of the image of something. So this first part here is a triviality. This is not something that's deep. This is a two-line argument. I'm just putting it here because it makes the theorem be nice. And then this is the hard part, which says that if R is, and so it somehow turns out to be a good idea to focus on this and that one. The other ones in between, you can also treat them, but they're just a bit more fiddly. So let me just focus on the 2-1 and the 3-1 case. And it says that up to isomorphism, there's a unique fully faithful representation. And so this is a classification because you just need to classify dominant functors, and then you have this part here is unique, and this needs to be classified, and those are well understood. These are in bijective correspondence with separable commutative algebras in the Drinfeld tensor of C. Anyways, it's a thing that people have studied and they know well. So this is a very satisfying answer to this question of whether representations can be classified. So now there is so now let me just get rid of a bit of stuff because there's just a bit too much here. Let's make a bit of space. This one I want to keep. Okay, so in order to talk about the next topic, I need to introduce a definition, which is the notion of, collect all these little magnets. Okay. Which is the notion of the commutant of one of these representations. So suppose I have such a representation, then the easy definition is to say it's just the endomorphisms of that representation, C-linear endomorphisms. But of course, we're working at the categorical level, and once you unpack things, they become a bit more bulky. And here I've unpacked it for you, just so that you see what it is. So an element of the commutant is an element of the ambient, Bim R, together with a half braiding, essentially something that exhibits the thing, exhibits X as commuting with everything coming from C. And now there's a theorem that I want to show you, a theorem from myself and Dave Penny's from a paper that we put on the archive very recently, that says, so there's a notion that has been around for some time of what it means for two fusion categories to be Morita equivalent. Essentially, it says it's formulated in terms of an invertible bimodule category. And so take C and D to be two Morita equivalent categories, and take C prime to be the commutant in the unique fully faithful representation. I mean, right, we talked about them being unique. That's this thing here. And similarly, take D prime to be the commutant of D in the unique fully faithful representation of D. Then these two are equivalent as tensor categories. So these were just Morita equivalent, and they become equivalent in a stronger sense. And so when I was finishing to write that paper with Dave Penny's less than half a year ago, I did not understand yet that this was really about representation theory of fusion categories. And now that I do, I can give you a 4-line proof of this thing. It's a bit embarrassing, but anyways, here it is. Here's a proof of this result. And it's not phrased in that way in the paper that we wrote, but here we go.
Andre?
Yes?
Sorry, I apologize, but isn't it a 5-line proof? Sorry to say. Well, yeah, apologies.
Touché. So, well, this equation is technically 1 line. So, for any reasonable notion of Morita equivalence, the category, which in this case is a 2 category of representations, should be the same. I mean, this is not the definition of Morita equivalence because the notion of two-category representations had not really been formulated as a thing, but here we go. This implies that. And then under that equivalence, you just need to check that the fully faithful representation goes to the fully faithful representation. And C prime is by definition the endomorphisms of that object. And under an equivalence of categories, endomorphisms go to endomorphisms, QED. So yeah. Now, what I would like to spend the rest of my time talking about is an application of these ideas, of this. I mean, so far what I've done is really just repackage things that other people have done in a language which I find appealing and which I haven't quite realized is a convenient way of talking about it. I mean, if you see, these theorems are fairly old, like Popper, 95, and then some people have sort of reworked them. In 15, they have reworked them. In 18, they have reworked them. So this is a well-reworked theorem. But the definition, the notion of representation as a phrase like that, and actually, more to the point, the two category of representations of a fusion category, that's something that people don't really talk about in those terms. So let me now do something with that. And I will, let's see.
By the way, Andre, I guess this is nothing like, there's no like double commutant here. There's no way to go back from C prime to C.
Yes, there is. So if you look at the action of C on R mod, the commutant is C prime, and the commutant of C prime happens to be, again, C, except you need to make it a tiny bit bigger. You need to allow infinite direct sums. So C was a fusion category which had only finite direct sums of simples as objects. That's just a tiny bit too small. So let's make it bigger by allowing infinite direct sums of objects. The same finite set of simple objects, but infinite direct sums. And then C and C prime become each other's commutants. So yeah, that's actually a thing that Dave Pennis and I have proven. And
does this give another way to see this implication then?
Which implication? This implication?
Yeah, the Morita equivalence, because I guess if this is the case, then whatever you get for C prime, you have to get back to C when you take commutant again.
Yeah, that's right. That's what I said. So indeed, the commutant of C prime is again C. But let me go on. So I want to talk a little bit about elliptic cohomology because okay. So there is a generalized cohomology theory that goes by the name TMF, that stands for topological modular forms, and which, well, sometimes when I talk about it, I use the terms elliptic cohomology, which is really a sort of less precise name, meaning there's many things that could be called elliptic cohomology, but there's only one thing that can be called TMF. And so this is a cohomology theory that was invented in the 90s by Mike Hopkins and Heinz Miller for, I mean, it's a bit of a long story. There's a way of constructing generalized cohomology theories starting from formal groups, but the assignment that goes from a formal group to cohomology theory is not completely functorial. They were thinking about the failure of functoriality and how if the formal group comes from an elliptic curve, then functoriality can be fixed. Anyways, it's a story that seems completely disjoint from what we're talking about so far. And in particular, rather disjoint from the formulation of the following important conjecture, which has been around for quite some time. So it was first formulated by Segal, and I mean, it wasn't formulated in a very crisp way, because if you see the date, 88, that's before TMF was even on the market. So then Stolz and Teichner spent a huge amount of time to try to make that to make some progress. And recently, Johnson-Freyd and David Gaiotto and Ed Witten, I mean, they really sort of have been testing this conjecture in very non-trivial ways and finding that so far, all the predictions of the conjecture seem to hold true. And the conjecture says that if you look at quantum field theories of a particular flavor, they have to be two-dimensional, they have to be supersymmetric with this particular amount of supersymmetry. And if you manage to make a topological space out of them, then that this should be a classifying space for TMF. And another equivalent way of saying the same thing is to say that if X is topological space, then a class in TMF X can be represented, or is the same thing up to homotopy, as a family parameterized by X of extended two-dimensional supersymmetric quantum field theories. And here maybe I should say extended means, so if you think of quantum field theories in the way Segal has taught us to think about quantum field theories, namely as functors from cobordism categories, then extended means that it's not just a category that we're looking at, but it's a two-category where you take your surfaces and you chop them in one direction, then you chop them again in a different direction. And so there's points and then one-dimensional cobordisms between them, and then two-dimensional cobordisms between those. And the quantum field theory is a functor out of that into a certain target category. So now here's a fact, which is maybe a bit of a controversial fact, but I'm just going to throw it at you like that anyways, which is that what an extended two-dimensional quantum field theory assigns to a point is a von Neumann algebra. And so I have a paper in 2013 where I show that in the case of conformal field theories, this really holds true. Namely, there is a meaningful way of extending conformal field theories to points where what you assign to a point is really a von Neumann algebra. And somehow I'm going to make the bold claim that this continues to hold true for all two-dimensional quantum field theories. Maybe all is an overstatement, like maybe I should say the unitary quantum field theories. I'm not exactly sure, but anyways, let me take it as a fact. Actually, let me sort of weaken it a little bit. Fact in quotes. Using that, here's one thing we can do. Suppose that I have such a family. One of the things you can do is to just forget everything and only remember what you assign to points. So this is a drastic forgetful operation, but it's one that I want to do nevertheless. And so what I'm telling you is that a toy version of TMF of X is bundles of von Neumann algebras over X. I mean, of course, that's not quite true, but if you think of the value of a point as being the most important thing that a quantum theory does, then a TMF class on X should be thought of as a bundle of von Neumann algebras over X plus some extra little structure, like whatever is needed in order to make these von Neumann algebras into full-fledged quantum field theories. So now here's something that those who know about elliptic cohomology might have heard, which is that one of the amazing things that Jacob Lurie told us about TMF is that TMF admits equivariant versions. Well, that's maybe not super surprising, but I mean, still hard to do. And moreover, admits so-called two equivariant versions. And this is a version of equivariance where the group of equivariants gets replaced by a two group. And if you remember at the beginning of my talk, I told you that there are certain types of fusion categories which correspond to two groups, namely these fusion categories where everything is invertible. Well, it's the very same flavor of two groups that is relevant for this generalized equivariance of TMF. And so now you see where I'm coming. So if you think of, okay, this is the last thing that I'm going to put. Whoops. Okay, sorry for that. That's a bit overambitious. So I told you that unitary fusion categories, they want to act on von Neumann algebras. And here we have bundles of von Neumann algebras, so we can say, okay, well, all these von Neumann algebras are going to be acted on by a fixed unitary fusion category, C. And then whatever extra structure I needed to add to this bundle of von Neumann algebras in order to go back along this wiggly arrow for get to get one of those, you can presumably do it carrying around this action of C. And so I would like to propose a conjecture that there exists a generalization of this two equivariant TMF, where you take, instead of a two group, you can take an arbitrary fusion category. And interestingly, I would like to note the following fact. So roughly a month ago, I went to a talk by David Gaiotto at Perimeter Institute, Canada. So thanks to coronavirus, I was there in the audience of that talk, where independently, he made the very same proposal, namely he sort of, in his talk, said, oh, there should exist a version of equivariant TMF where the group of equivariants is replaced by a fusion category. And and his reasoning was not along the same lines as the reasoning which I have presented here. And so I find that just to be an interesting perspective about things. My guess is that there's not much chance of proving this before having sorted out this important conjecture about the relationship between TMF and the space of all quantum field theories. So yeah, so probably it's going to be something difficult. But anyways, I thought that for the purpose of giving a talk, it was good enough, and then that I just wanted to share that idea. Well, on those words, thank you very much.